66 million years ago, a rock 10 kilometers wide hit the Yucatan Peninsula at 20 kilometers per second. The energy released was 2 million times more powerful than the largest nuclear weapon ever detonated. It ended a dynasty that had lasted 165 million years, and somebody somewhere maybe missed it. That's the premise anyway. The universe spent 4 billion years building dinosaurs, then destroyed them, and the whole show might have been for an audience that hasn't arrived yet. That's a crazy thing to say. But buried inside it is a real question about physics, about why complexity exists at all, whether it's inevitable, and what the universe is actually doing with its time. Now, I want to be clear about something before we go further. When people hear a phrase like the universe created dinosaurs for aliens, they reach immediately for one of two responses. Either they laugh it off as nonsense, which is the intellectually lazy move, or they nod along because it sounds cosmic and deep, which is worse. What I want to do is take that sentence seriously as a physics question. Strip the poetry out of it and ask, what would it actually mean for the universe to produce something? What are the physical mechanisms? What do we know? What are we guessing? Where does honest inquiry end and storytelling begin? Because there is real physics in that question. Strange, verified, quantitative physics. And when you follow it carefully, you end up somewhere genuinely surprising, not because the universe is mystical, but because it turns out to be far more structured than anyone expected. Let's start with what we actually know happened. The Earth formed about 4.54 billion years ago from a disk of gas and dust orbiting a young star. We know this from radiometric dating, measuring the decay of uranium-238 into lead-206, which happens at a known measurable rate. The solar system condensed from a cloud of gas that was itself the remnant of earlier stars. Stars that had lived, burned through their hydrogen, fused heavier elements in their cores, and exploded, scattering carbon, nitrogen, oxygen, and iron into the interstellar medium. You are made of atoms forged in stellar explosions. That is not a metaphor. The carbon in your cells, the oxygen in your lungs, the iron in your blood, those atoms were nucleosynthesized inside stars that died before the sun was born. What you are physically is stardust that has organized itself into something capable of knowing it is stardust. That is either unremarkable or the most remarkable thing in the universe, and I genuinely don't know which. The oldest evidence of life on Earth comes from stromatolites, layered sedimentary structures built by photosynthetic bacteria, preserved in Western Australia, dating to approximately 3.5 billion years ago. There is tentative chemical evidence, carbon isotope signatures, in ancient Greenland rock formations, suggesting life may have appeared even earlier. The point is, within perhaps 1 billion years of Earth forming, life was already running. In geological and cosmological terms, that is fast. Either life starts quickly when conditions allow it, or we got extraordinarily lucky with our timing. We cannot tell which from one example. Here is the first place I want to be honest about our limits. We do not know how life started. I want to say that plainly, because it is true, and because it matters. We have excellent hypotheses. The RNA world hypothesis, the idea that self-replicating RNA molecules preceded both DNA and proteins, is the most experimentally developed. In 1953, Stanley Miller and Harold Urey ran an electric discharge through a flask of water, methane, ammonia, and hydrogen, their best approximation of early Earth's atmosphere, and produced amino acids in a week, the building blocks of proteins made from scratch from chemistry alone. That was a genuinely important result. But producing amino acids is not producing life. The gap between a flask of interesting chemistry and a self-replicating, metabolizing, membrane-enclosed living cell is enormous, and we have not bridged it. What we have is pieces. The pieces are suggestive. The full sequence is unknown. Anyone who tells you the origin of life is essentially solved is either confused or selling something. What we can say with confidence is this. The chemistry that precedes life appears to be common. The Murchison meteorite, which fell in Victoria, Australia in 1969, contained over 90 different amino acids, only 19 of which are used in Earth life. Complex organic molecules, including amino acid precursors, sugars, and alcohols, have been detected in interstellar molecular clouds using radio telescopes. The building blocks are not rare. They are scattered across the galaxy, manufactured in the hearts of dying stars, and seeded through space by stellar winds and explosions. The universe makes this chemistry readily. What we don't know is how readily it takes the next step. Now let's talk about the dinosaurs, because this is where the timeline becomes genuinely strange and the question of purpose starts to bite. Dinosaurs appeared approximately 230 to 240 million years ago during the Triassic period. They didn't arise in comfortable conditions. They arose in the aftermath of the Permian-Triassic extinction, the most severe mass extinction in Earth's history, which wiped out roughly 96% of all marine species and about 70% of terrestrial vertebrate species around 252 million years ago. The ecosystems were largely empty. Dinosaurs filled them, diversified enormously, and for the next 165 million years dominated terrestrial vertebrate life on Earth. Let me put that in perspective. Homo sapiens has existed for perhaps 300,000 years. Our entire history, every civilization, every war, every painting, every equation fits inside 0.18% of the time dinosaurs spent on this planet. If you compress dinosaurs' tenure to a single calendar year, our entire species appears in the last 16 hours of December 31st. We are newcomers. The dinosaurs ran the show for a period so long it barely registers on our intuitions, and then the rock arrived. We have known since 1980, when Luis Alvarez, his son Walter, and colleagues Frank Asaro and Helen Michel published their landmark paper, that a major impact event ended the Cretaceous period. They found a thin layer of iridium, a metal rare on Earth's surface but common in extraterrestrial objects, distributed globally at the Cretaceous-Paleogene boundary. The concentration was about 30 times higher than background levels. The only plausible explanation was a large asteroid impact that vaporized and distributed the impactor's material worldwide. The impact site, the Chicxulub structure, was identified in 1981 by geophysicist Glenn Penfield using gravity and magnetic survey data from the Gulf of Mexico. The crater is roughly 180 kilometers in diameter, centered on the Yucatan Peninsula. The impactor, estimated at 10 to 15 kilometers across, struck at approximately 20 kilometers per second. The energy released was on the order of 100 teratons of TNT. That is a number so large it resists intuition. The Soviet Tsar bomba, the most powerful nuclear weapon ever tested, released about 50 megatons. The Chicxulub impact was roughly 2 billion times more energetic. The immediate effects cascaded: a thermal pulse, global wildfires from re-entering ejecta, sunlight blocked for months to years by suspended dust and sulfate aerosols, collapsing photosynthesis and the food chains dependent on it. Roughly 75% of all species on Earth vanished, including every non-avian dinosaur. Birds survived. That is worth saying directly. Birds are dinosaurs. Not metaphorically, not loosely. Birds are theropod dinosaurs phylogenetically nested within the dinosaur family tree. When you watch a pigeon walking across a sidewalk, you are watching a living dinosaur. The line connecting Tyrannosaurus rex to that pigeon is unbroken. The Alvarez team's discovery of the iridium layer and the subsequent identification of Chicxulub gave us the mechanism for the transition. The rock didn't end dinosaurs. It ended the non-flying ones. Now here is the question I actually want to examine. The claim the universe created dinosaurs for aliens includes the word created, which implies direction, intention, agency. But the Chicxulub impactor had no agenda. It was a rock on an orbital trajectory determined by gravitational mechanics, perturbed over millions of years by the accumulated gravitational tugs of Jupiter, Saturn, and other bodies until its path intersected Earth's. No purpose, no message. The same physics that built 165 million years of complex life also delivered the rock that ended most of it. So what do we mean when we say the universe creates anything? This is where thermodynamics enters, and it is almost always explained badly. The second law of thermodynamics says that in a closed system, entropy tends to increase over time. People translate this as things fall apart, or disorder increases. That captures something but misses the operational meaning. Entropy is a count of the number of possible microscopic arrangements consistent with what you observe. A highly ordered state corresponds to a very small number of arrangements. A disordered state corresponds to an astronomically larger number. The system moves toward higher entropy, not because of some force-compelling disorder, but because there are simply vastly more ways to be spread out than compressed. It is probability, not preference. The apparent paradox: a living dinosaur is an extraordinarily ordered structure. Proteins folded into precise configurations, DNA encoding functional information, metabolic networks of enormous complexity. How does this arise in a universe running toward disorder? The answer is that the second law applies to closed systems. Earth is not a closed system. The sun pours approximately 174,000 terawatts of radiation onto Earth continuously. Life captures a fraction of that, about 0.1% through photosynthesis, uses it to build local order, and dumps waste heat into space. Total entropy of the Earth-Sun system still increases, but locally, a sustained flow of energy from a hot source to a cold sink drives the assembly of complex structures. Erwin Schrödinger described this precisely in What is Life in 1944. Living organisms maintain internal order by continuously consuming free energy from their environment. Life doesn't violate thermodynamics. Life is a thermodynamic process, a sophisticated one running on stellar output, but thermodynamics nonetheless. Wherever there is a sustained energy gradient, a rocky planet at the right distance from a stable star, physics permits the local construction of ordered structures. That condition is not rare. It exists wherever stars and planets exist. Now I want to go somewhere that makes some physicists uncomfortable, but is genuinely important: the fine-tuning problem. The universe is governed by a set of physical constants, numbers we measure but cannot, with our current understanding, derive from anything more fundamental. The gravitational constant, the fine structure constant, approximately 1/137th, which governs the strength of electromagnetic interactions. The ratio of the proton mass to the electron mass, about 1836. The cosmological constant, governing the large-scale expansion of the universe. These are what they are. We measure them. We don't know why. Here is what is strange about them. Small changes to some of these constants would produce a universe in which complexity and therefore life could not arise. If the strong nuclear force were about 2% weaker, protons would not bind into nuclei, and there would be no chemistry. If the cosmological constant were much larger, the universe would have expanded too rapidly for gravity to assemble galaxies and stars. The universe would exist, technically, but it would be a thin, structureless gas, expanding forever in the dark, producing nothing. Fred Hoyle confronted this directly. In 1953, Hoyle was working on stellar nucleosynthesis, how stars manufacture heavy elements from hydrogen and helium. Carbon is the backbone of all known life. Carbon is produced in stars through a reaction in which 3 helium nuclei collide and fuse. For this reaction to happen at a rate sufficient to produce the carbon we see in the universe, carbon-12 must have a nuclear energy resonance, a specific excited state at approximately 7.65 megaelectron volts. Hoyle calculated this before it was measured. He argued the universe contains carbon. We are made of carbon, therefore this resonance must exist. When experimenters at Caltech checked, led by William Fowler, the resonance was precisely where Hoyle said it had to be. Hoyle later said this result shook his atheism. I don't think it proves anything about design, but it is a genuinely remarkable coincidence, and coincidence may not be the right word either. What Hoyle found is that the constants of physics are tuned within narrow windows to permit carbon to exist in the universe at all. This is one of several such coincidences in the fundamental constants. What does it mean? The honest answer is, we don't know. Several possibilities are seriously discussed. One is that we live in an ensemble of universes, a multiverse, in which the physical constants vary, and we necessarily find ourselves in one that permits our existence because we couldn't be in any other kind. This is the anthropic principle, used as a selection effect, not a mystical claim. Another possibility is that there is a deeper theory, not yet found, from which the constants can be derived, making them not arbitrary at all, but the only values consistent with some more fundamental structure. A third is pure contingency. The constants happen to be what they are, we happen to be alive. And these two facts are connected by nothing except the obvious logical point that dead universes produce no observers. I find the fine-tuning problem genuinely interesting, precisely because it doesn't have a clean resolution. It is not mysticism. It is a real quantitative puzzle about why the numbers that govern physics take values compatible with complexity. We notice the puzzle. We don't have the answer. Now the alien question. Let's take it seriously. In 1961, the radio astronomer Frank Drake gathered a small group at the National Radio Astronomy Observatory in Green Bank, West Virginia. He wrote an equation on a blackboard, what we now call the Drake equation, designed to estimate the number of currently detectable communicating civilizations in our galaxy. The equation multiplies together a chain of factors: the rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those with habitable planets, the fraction where life arises, the fraction where intelligence develops, the fraction that produce detectable technology, and the lifetime of such civilizations. Drake's first attempt at a radio search, Project Ozma, in 1960, pointed a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for narrowband radio signals at 1420 MHz, the frequency of hydrogen emission, long proposed as a natural communication channel. He heard nothing from either target. In 1977, an Ohio State University radio telescope recorded the WOW signal, a burst of narrowband radio emission lasting 72 seconds at 1420 MHz, arriving from the direction of Sagittarius. It was so far outside the noise that the astronomer who spotted it, Jerry Ehman, circled it on the printout and wrote WOW in the margin. It has never been detected again. It remains unexplained. Most astronomers consider natural or terrestrial explanations more probable, but it has never been definitively identified. Here is the uncomfortable truth about the Drake equation. In 1961, almost every factor in it was unknown. We knew approximately how fast stars form, about 1 to 3 new stars per year in the Milky Way. We knew nothing about the fraction of stars with planets. We had detected 0 planets outside our solar system. Every estimate beyond the first term was essentially a guess dressed in mathematical notation. Drake knew this. He used the equation as a framework for organizing ignorance, not as a calculator. What we can say with more confidence is the first few terms. We have measured stellar formation rates. We have good models of planetary system formation, based on the structure of our own solar system and the theoretical requirements for planetary accretion. Many astronomers in the 1970s and 1980s believed planetary systems should be common around sun-like stars. The theoretical argument was solid. The direct evidence was not yet there. The silence in the radio spectrum, though, that is data. 28 years of searching from Project Ozma in 1960 to today has produced no confirmed extraterrestrial signal. The Fermi paradox, Enrico Fermi's 1950 lunch table observation that the universe is old enough and large enough that if technological civilizations are common, they should be everywhere and detectable, and yet we see nothing, remains unresolved. We have looked. We have heard nothing confirmed. This could mean many things. The universe may be mostly empty of technological life, or the signals may be there and we are not listening in the right way at the right frequencies with sufficient sensitivity, or technological civilizations are brief, they arise, and within a geologically short time they either destroy themselves or stop transmitting in ways we can recognize. We cannot yet distinguish between these possibilities. The question of whether life exists elsewhere has to be the most important unanswered question in science, not because of what the answer will feel like philosophically, though it would feel like quite a lot, but because either answer transforms our understanding of the universe. If life is common, the history of Earth is one of billions of similar histories, and the emergence of complexity from chemistry is a robust feature of the universe's physics. If life is rare or we are alone, then something about this planet or this moment in cosmic time is extraordinary in a way we do not yet understand. Let me come back then to the question itself. The universe created dinosaurs for aliens, and say what is actually defensible and what remains genuinely open. What is defensible? The universe has laws that permit complexity. The constants of physics are compatible with nuclear chemistry, with stars that burn steadily for billions of years, with planetary systems, with liquid water, with carbon-based chemistry, and with the eventual appearance of organisms like dinosaurs and like us. This required specific physical conditions, the fine-tuning we discussed, but whether those conditions were arranged or are simply the ones we happen to find ourselves in, we cannot determine. The observation is solid. The inference to design is a choice, not a measurement. What is defensible? The ingredients for life appear to be distributed throughout the galaxy. Organic chemistry is not Earth-specific. The chemistry appears to be common. What we genuinely don't know is how often it takes the next step to self-replication, and then to cells, and then to multicellular life, and then to cognitive complexity. We have one example. One is not enough to calculate a probability. What remains genuinely open, whether the silence of the cosmos means we are alone, or rare, or simply early, or searching wrong, whether the great filter, whatever step in the development of civilization is catastrophically difficult, is behind us or ahead. These are open questions in the most honest sense. We have not answered them, and the answer will matter enormously. When someone says the universe created dinosaurs for aliens, the interesting version of that claim is this: the same physical laws and cosmic processes that produced 165 million years of dinosaurs on Earth are running right now on an unknown number of other worlds, On some of those worlds, perhaps complex chemistry has begun. On some fraction, life. On some smaller fraction, the kind of complexity that looks up and wonders. We don't know how large those fractions are. We are, right now, at the earliest stages of being able to find out. So let's return to that rock. One final time. 66 million years ago, 10 kilometers of rock hit the Yucatan at 20 kilometers per second. No purpose. No message. Orbital mechanics run to their conclusion. It ended 165 million years of one experiment in terrestrial complexity and cleared the ecological space for another. In the aftermath, small mammals diversified, primates appeared, and eventually here we are, the first organisms on this planet, capable of asking why the rock arrived, what the dinosaurs were, and whether anything else anywhere is running the same experiment. The universe didn't create dinosaurs for aliens. The universe ran its physics. The physics permitted dinosaurs, and the impactor, and the mammals that followed, and us. And it is running on billions of other worlds right now with no guarantee of outcome. Whether that physics reliably produces observers, whether the universe is the kind of place that keeps generating things capable of asking these questions, that is genuinely unknown. That is not a failure. That is exactly where honest inquiry leaves you when it has done its job, at the edge of what we know, facing a question that is real, that matters, and that we might actually be able to answer. That is worth considerably more than a comfortable story.